Hello, everyone, and thank you for attending my presentation that will be dealing with an investigation on ejector design for CO2 heat pump applications using the Dymola software. So the layout of this presentation is going to be as follows. First, we will get through, well, what is an ejector? Why would we be using such a device into heat pump systems? And what are the challenges that come along with it? Then we will review a bit of theory, and I will explain our methodology. We will have a look at the in-house ejector model that was implemented for this work. Then we will briefly introduce the Dymola software and the TIL library, which is the thermal system library, which was used to model the heat pump system. Next, I will present the CO2 heat pump system that was simulated, and we will look at the results of the investigation that focuses on ejector sizing at fixed geometry. And lastly, the presentation will obviously end with some conclusions. So first of all, what is an ejector? Well, an ejector is a passive device that is used to suck and compress fluids. As you can see on the schematic, the idea is that a primary fluid at high pressure will be discharged into a primary nozzle. And by doing so, the primary fluid will suck up and compress a secondary fluid that is at low pressure. So the two streams will mix up and interact into the mixing chamber and end up at the discharge of the ejector with an intermediate pressure. So ejectors are used for a variety of applications. For example, in the food industry, where they are used mostly to create vacuum, for desalination applications, in the aerospace industry. But I would say their main application is to be integrated into heat pump systems. So why would we be using ejectors in heat pump systems? Well, the short answer is because it allows us to recover part of the exergy loss that occurs at the expansion level of the heat pump cycle. To be more precise, let's look at the diagram on the right. And we can see that instead of discharging the high pressure refrigerant into a classical expansion valve, it is rather expanded into an ejector, which allows us to pre-compress the low pressure refrigerant that comes from the evaporator. And so we have an intermediate pressure at the inlet of the compressor, which means that to produce the same heating or cooling power, we will require a smaller compressor. So in other words, the coefficient of performance of the cycle will be higher. In addition to that, we can also know that ejectors have no moving parts. Therefore, they are low cost, they need very low maintenance, and they can work with a variety of fluid. Just as we saw, they can use low-grade energy as input, and they can perfectly work with two-phase flows. So what are the challenges? Well, ejector design is notoriously difficult because of the complexity of the internal flow. And to illustrate that, I propose to have a look at the two photographies on the slide. The first one is a visualization of the flow within an air ejector, where one can observe the complex shockwave patterns, boundary layers, and turbulence effects. And on top of that, if we are dealing with CO2 flows, we have the additional issues that experiments are very complicated because CO2 ejectors are very small, and the fact that the flow is two-phase. Indeed, as you can see on the bottom picture, the primary flow flashes into the primary nozzle. Therefore, we can observe a cloud of two-phase CO2 that actually interacts with the secondary flow that is actually superheated gas. So bottom line is that to properly design ejectors, one should account for those complex flow interactions, which is not straightforward. So let us now go through a bit of ejector theory that will help us to understand what follows. So when we assess ejector performance, we very often refer to the so-called characteristic curves of the ejector, which are curves of the entrainment ratio as a function of the outlet pressure with obviously fixed inlet condition. And so the entrainment ratio is just simply the ratio between the secondary mass flow rate and the primary mass flow rate. And so you can see that we can define three operating regimes depending on the range of outlet pressure. If we start from a low outlet pressure and that we start increasing the pressure, we see that at first the entrainment ratio, which is nothing else but an image of the total mass flow rate within the ejector, well, it remains constant. We call this the undesigned regime, and we say that the ejector is double choked. Then, if we keep increasing the pressure, we eventually reach the so-called critical point. And after this point, we see that the entrainment ratio goes down with the outlet pressure. And we call this regime the off-design regime. Eventually, if the pressure gets too high, we reach the backflow mode, which corresponds to a flow reversal into the secondary inlet. And so this is a malfunction, of course. Another important thing to note is that when we are analyzing and predicting ejector performance, determining the critical condition is actually crucial. And the classical way of doing so, which is also referred as using the Fabry choking criterion, is to impose that primary and secondary streams must reach Mach 1 at their respective throats. So for the primary stream, this is rather straightforward, but for the secondary stream, the choking is supposed to be occurring at the so-called hypothetical throat, which is an aerodynamic throat that is formed by the expansion of the primary stream into the mixing chamber and the ejector wall. But actually, it was recently found by our research team that this Fabry choking criterion may actually not be the best. And to illustrate this, let's have a look at this graph, which is a graph of the entrainment ratio as a function of the mixing pressure. So the pressure, that is the pressure at the location of the hypothetical throat. We can see that the Fabry choking criterion does not lead to the maximization of the mass flow rate within the ejector, which is really the real physical interpretation of choking. And so instead, a better choking criterion can be used, which is called the compound choking criterion. And that is actually equivalent to maximizing the total mass flow rate within the ejector. And so it is important to note at this point that this is the criterion that was used for this work. So let us now review the different tools that were used in this study. First, the ejector model that was used is the model that was recently published by our team, which was originally a Python model and that has been re-implemented into the Modelica language in order to make it work with Dymola. So this is a thermodynamic model. Therefore, the ejector is discretized into several sections, and the classical conservation equations are solved within each of those. In addition, the model contains 5 efficiencies that are used for calibrating purposes. And as I said before, we use the mass flow rate maximization criterion for double choking. So using those efficiencies, the model was calibrated onto the CO2 experimental data of Zhu et al., which is consistent with the typical operation of a transcritical CO2 heat pump system. And a good fitting was obtained for the 3 sets of experimental data by using only constant efficiency values, and therefore it was chosen to keep those constant as well during the following simulations. As I mentioned before, the software that was used for the simulation is Dymola, which is a simulation tool based on the Modelica modeling language. And so Dymola can be used to solve a variety of problems from various scientific domains. But in our case, we want to solve thermal systems, and therefore we worked with the TIL library, which comprises a range of Modelica objects, ranging from compressors to heat exchangers. And so the user can then graphically assemble his cycle and run it without even having to interact with code. And so the TIL library also comes with two ejector models. The first one is based on the definition of a constant ejector efficiency. And the second one defines a linear relation between the entrained mass flow rate and the outlet pressure. However, it was found that those two models have limitations, which is why the in-house ejector model was implemented. And to show you those limitations, I invite you to have a look at the two graphs on the slides, starting from the left one. Those are actually the characteristic curves produced by the two TIL models and the in-house model. And as we can see, both TIL models are unable to properly model the on-design plateau and the rapid decrease in performance under the off-design regime. And on top of that, as you can see, if the operating condition change from the calibration once, the TIL models do not evolve in the right way. Indeed, if we look at the graph on the right, if the primary pressure is lowered, the curve of the in-house model is shifted up and to the left, which is what would be physically expected, whereas the TIL models are unable to follow the same trend. Okay, it is now time to go over the studied cycle, which is a 3 pressure levels air water heat pump system that is typically used to generate hot water to heat up residential buildings. And so this cycle comprises 3 loops: a water loop, an air loop, and a CO2 loop. And the purpose of this system is to transfer heat from the air loop to the water loop via the CO2 loop. So starting from this point, the gas CO2 is compressed. It is cooled down in the gas cooler, and it is then expanded into the ejector, where it flashes into the primary nozzle and mixes with the secondary. The flow at the outlet of the ejector is also two-phase and is partially evaporated into the high-pressure evaporator. The flow is then separated. The gas phase goes back into the compressor, obviously, and the liquid phase is further expanded into an expansion valve. It is then fully evaporated and fed into the secondary of the ejector. And so the goal of this study is actually to investigate the influence of the ejector size on the performance of the global system. So during the simulation, only the ejector size is varied, and so the geometry on itself is kept constant. So in other words, what we want to know is, well, what size should have our ejector to produce a given flow rate of hot water while having the best coefficient of performance. So let's first have a look at the pressure at the inlets and outlet of the ejector. And note that all of the graphs are here a function of the ejector size, which is represented here by the non-dimensional throat area of the ejector. We can observe that as the ejector gets bigger, the primary pressure gets lower. And that is because, well, when the ejector size is increased, as the ejector is supersonic, the primary mass flow rate also increases. And so this means that to maintain the same power transfer in the gas cooler, the density should get lower, which roughly translates into a primary pressure decrease. In addition, we can observe that as the ejector gets bigger, the discharge pressure gets higher, whereas the secondary inlet pressure gets lower. And this is a result of the expansion in the constant area expansion valve. Next, as I'm sure some of you noticed, there are actually kinks in the curves for low ejector sizes. And this is actually due to the fact that at those operating conditions, with this ejector size, the primary flow rate is very small, so that the temperature at the CO2 outlet of the gas cooler tends to reach the ambient temperature, and the power transfer potential from the CO2 loop to the water loop then becomes hindered by the small temperature pinch of the exchanger. And this actually translates into a shift in the cycle regime that we can see. So finally, let's have a look at the performance parameters of the cycle and of the ejector. We can see that there indeed exists an ejector size that maximizes the coefficient of performance of the cycle. But interestingly, there is no apparent correlation between the different performance parameters of the ejector and the cycle. We see that the maximum entrainment ratio does not correspond to the maximum of COP, and that the compression ratio actually does not have a maximum. So in addition to that, we see that this maximum COP does not correlate with the ejector critical point, which is located at the intersection between on and off design regimes. And the ejector is rather operating well under on design regime at the maximum COP. And so this really goes to show that it is important to study the cycle in its whole when we are dealing with ejectors. So in conclusion, we saw that the ejector models of the TL library were limited, and therefore an in-house state-of-the-art ejector model was implemented into Dymola. This model was calibrated onto experimental data and used to simulate a 3 pressure levels ejector heat pump system. It was found that there exists an ejector size that maximizes the COP of the cycle, and that for this present cycle, there is no apparent correlation between the ejector performance and the COP, as is commonly the case. Therefore, it would be interesting in the future to study in more details the dependencies of ejector operating regime and maximum COP. Also for more complex cycles, and also it would be interesting to see how this optimum COP can vary with the ambient conditions. This being said, I thank you very much for your attention, and I will gladly answer your questions if you have any.